back. In the previous lesson we learnt about the various sampling techniques. Now we will go through an important concept known as central limit theorem. This is one of the cornerstones of statistics as well as Lean Six Sigma analysis. Central limit theorem is linked with normality of the data along with the size of the sample. As we have seen so far, the data set collected from a process may or may not represent a normal distribution. However, it has been seen that when a large enough samples are drawn from any distribution, the distribution of the sample means approaches a normal one. This usually happens when number of samples drawn is more than 30. Though it may not be always the case, the more the distribution resembles normal, the fewer samples are needed to create normal sample mean distribution and confirm the central limit theorem. The reverse logic of this is also true. The more the distribution deviates from normal, greater number of samples are needed to demonstrate the central limit theorem. Let us understand with the help of an example, what is the impact of sample size on the distribution. If we take 20 spindles length and plot them, it will form some kind of distribution. Now, we will take samples of individual observations and calculate mean of each of the sample. We'll keep taking many such samples which are actually a set of samples taken from the distribution. For example, N1 with 5 spindles, N2 with 5 spindles, and so on so forth. If we take 100 such samples, calculate their means and plot those sample mean values on a frequency histogram, we will find that the distribution is approaching to normal. This is irrespective of the distribution that is taken by individual values. This is what central limit theorem is. It says, as the sample size becomes large, this new distribution, the sample mean distribution, will form a normal distribution, no matter what the shape of the population distribution of individuals is. Now if we further increase the sample size, to say 1000, and plot this distribution where each of the dots represent an incidence of a sample mean, we can see that the distribution has become a normal distribution. So, we can say that the distribution of the sample means approaches to normal when sample size n becomes too large or approaches to infinity. Usually, it is found that when n is more than 30, the distribution of sample mean approaches to normal. We will see this phenomenon with more examples now. We should understand that there is always a chance of error in conclusions when we do analysis on samples in comparison to studying whole population. There are possibilities of error in measurements, as that of gauge repeatability and reproducibility. Or, there may be a chance that we are not measuring what actually should be measured. Environmental factors are leading to incorrect observations. There is also a possibility that error is introduced due to sampling. There may be error introduced due to sampling procedures that we choose. For example, choosing systematic sampling. Another possibility is due to the difference among samples drawn randomly from the population just by chance. This last type of error that we just discussed is accommodated in statistical analysis. To understand the link between the sampling error and central limit theorem, we'll make use of randomly generated spindle length data now. So, we'll create some data to understand impact of sample size. This data is also available in the Analyze Data workbook. To create random data of spindle length in centimeters, we'll go to Sigma Excel, Random Data and select Normal. In the dialog box, we'll fill the details as given here, and click OK. This will generate our normally distributed data for hypothetical population. Now we'll generate sample data from this population data. We'll create 5 number of data sets each for sample size of 5, 15 and 30. For this, go to Sigma Excel, Data Manipulation, select Random Subset, select Data, and first time put 5 in the dialog box as shown here. It'll generate a random data picked from the population that we had just created. Now we need 5 such data samples with n is equal to 5. We'll call the dialog box and repeat the steps for 4 more times. Then we need to arrange the data on sheet as shown here. Similarly, we'll create more data for the sample size of 15 and 30. It'll look like this. We'll calculate the mean and standard deviation for population and samples 1 to 5, and compare the sample statistics to the population. We can see as the sample size increases, the difference in their individual means and standard deviation decreases. To check it, we quickly calculated the ranges of the datasets with sample size 5, 15, and 30 respectively. We can note here that the range in mean and standard deviation values for n equals 30 has reduced drastically in comparison when n is 5. This explains the chance of sampling error when the sample size is small and when it is large. Larger the sample size, sampling error gets lesser. Now we'll move further towards establishing the central limit theorem. Instead of taking individual values for analysis, we'll take samples and plot the distribution of sampling means. We'll create a hypothetical dataset, with any distribution, to create the samples. Once the data is created, we add a column with averages of each row. These are the means of randomly generated samples, which are not normally distributed. Since n is 10 here, we now check whether the sample mean distribution is normal or not. We'll perform descriptive statistical analysis. This histogram and Anderson dialing test suggests that the sample means are normally distributed. Just to recall, we know that if the p-value is more than 0.05, the data are normal enough for most statistical analyses purposes. We can compare the distribution of sample means with the histogram of one sample with 10 individual observations, and also with sample means where the sample size, n, is equal to 4. We can see as the sample size n and number of trials, that as the number of sample means are increased, the distribution tends to normality. We should again note here that sample means and sample size will behave in similar fashion, that is, when n tends to infinity, the distribution in both the cases will approach to normal. Another thing to ponder upon, what if sample size is 1? We'll leave this up to you to experiment. Get in touch with us for any help. Thus, to summarize what we observed so far, as the sample size, n, increases from 1 to 5 to 10 to infinity, there are 3 points to note. Center remains the same. The standard deviation or spread decreases. The shape of the distribution changes. It tends to become normal. The central limit theorem says that, if all possible random samples, each of size n, are taken from any population with a mean and standard deviation, the distribution of sample means will have mean, mu x bar is equal to mu x. That is, the mean of sample means would be equal to population mean. And standard deviation of sample means, sigma x bar, will be equal to standard deviation of the population, sigma x, divided by root n. This also shows that when n will increase, the standard deviation or standard error will decrease. The sampling distribution of sample means will approximate to normal. The degree to which a sampling distribution approximates to normal becomes greater as sample size n becomes larger. From the exercises we did in this lesson, we can say that the sample means will be normally distributed when the actual population is normally distributed, or will be approximately normal for samples of size 30 or more when the actual population is not normally distributed. In our examples, we should have noticed that when n increases, the standard deviation of sample mean decreases. So there is a way to find standard deviation of sample means, which is also called as standard error. With experiments, it has been found that the variance of the sampling distribution of sample means is equal to the variance of the original distribution of the population, divided by n. It can be denoted by this equation. Note that standard deviation is the square root of the variance. In most of the cases we don't know the population variance, thus we make use of sample variance, s square. The standard deviation for the distribution of means is called the standard error of the mean, and is defined as Sx bar is equal to Sx divided by root n, where Sx bar is standard error of the sample means, Sx is standard deviation of the individuals, and n is the sample size. This equation has come from the above equation only. The difference is that in the first equation we talked about population variance, and the second equation is for samples and standard deviations of samples and sample means. So when we convert variance to standard deviation, we take square root on both the sides. This standard deviation of the sampling distribution of the sampling means is also called standard error. The significance of this whole theorem is that we want to reduce the sampling error in estimating about population. It has been seen that as the sample size reaches to 30 and further, the rate of change in standard error approaches to zero. At this point, the T and Z distribution also become almost equivalent. This is the reason why a sample size of 30 is mostly talked about. But we must know that just by taking a sample size of 30 doesn't necessarily make a distribution normal. We must test for normality and ascertain the observations. So far we covered the fundamental concepts of inferential statistics like sampling and central limit theorem along with errors etc. Now we will move to the next unit in which we learn about the hypothesis testing. Here we come to an end to this lesson. Should you need any support, feel free to contact us. Thanks for watching this video, and see you in the next lesson.